Good evening. Thank you for joining us tonight. I'm Deborah Rollison of the U.S. Naval Research Laboratory, and it's been my privilege over the last 4 years to chair the subcommittee that selects the MRS Mid-Career Researcher. And our award for 2015 is going to Seth Marder. I'd like to thank the governance of the Society for recognizing that the mid-career was an overlooked phase in terms of awards and recognition. And we know that because this year we had over 70 candidate application packages, 7-0. So not only was it a privilege, it was a lot of work. But the good message, the good take home here is that the breadth, the quality, the innovativeness is everything the society seeks to engender and to recognize. So it's clear we've got a lot of great leaders in materials research. And I'd also like to thank Aldrich Materials Science because they are the sponsor of this award. They're in booth 412 down at the exhibit. They're celebrating the 10th anniversary of Materials Matters. So pop by, pick up your favorite flavor of Materials Matters, wangle a cup out of them. So let's get to Seth because we don't want to eat into his time. Seth Marder, professor at Georgia Institute of Technology, is receiving this honor for establishing fundamental relationships between the chemical structure of organic molecules and their optical and electronic properties, thereby profoundly impacting how the scientific community designs optimized molecular structures for use in nonlinear optical applications. Now, Seth is at Georgia Tech, but he wears a lot of hats. He is the Georgia Power Chair of Energy Efficiency. He's the Regents Professor of Chemistry, and he's a Professor of Materials Science and Engineering. He has over 400 peer-reviewed papers, and somebody cares because they've got over 28,500 citations. So his work is leading his field. He's also a fellow of 6 societies, including the Materials Research Society, and he's actually done a lot of governance work. He's helped chair a materials-focused subcommittee for the Department of Commerce, and 30 patents plus, so his great research is leading into new technology, and those companies have gotten bought out by a Fortune 500. So tonight, he's going to talk about the design of materials for third-order nonlinear optics, and he's going to tell us how you make your organic molecule do what it needs to do with light. Professor Marder.
Okay. Well, thank you very much, and thank you to the Society for bestowing this honor on me. I was delighted to find out that I am only mid-career. I don't know if my wife would agree, but that's okay. So what I'm going to do is I'm going to tell you about materials for third-order nonlinear optics. Third-order nonlinear optics is not something that jumps off everyone's tongue. And so what I'm going to try to do is, for the people who are not as aware of this field, tell you a little bit about the basic phenomena in the field, the origins of third-order nonlinear optical effects, and then walk you a little bit through how we design molecules and materials for this. Now, I've been around for a long time, and I have been fortunate to work with a lot of talented graduate students, postdoctoral researchers, and visiting scientists who have been in my group working. This is specifically in the area of nonlinear optics, and these people have done a lot of the work. And I've also been part of a collaborative team of people from the United States and all over the world, and most particularly my colleague Joe Perry, Jean-Luc Breda, who is here in the audience, and Bernard Kiplin, who we've worked together as a team of people who are doing theory, synthesis, and characterization work so that we can get an overall picture of things. We've had sustainable support from various funding agencies, and we're very, very grateful to them. So, with that said, I'll start with an introduction to third-order nonlinear optics, and then I'm going to talk about imaginary third-order nonlinear optics and real third-order nonlinear optics. And these are two aspects of the same kind of physical process, but they give rise to very different effects, both of which can be quite useful. Let's just start very quickly. If you have a molecule or an atom in an electric field and you have an oscillating electric field, you'll set the electrons in the atom oscillating, and you can do a simple plot of the induced polarization, the dipole moment in the case of a molecule, as a function of the applied field, and it will be a linear plot if the molecule has a very simple linear restoring force for the electrons around the nuclei. And so at the molecular level, you can write an equation that describes that. Mu induced equals alpha E, where E is the electric field and alpha is the linear polarizability. At the materials level, you can write a polarization density, which is the first order susceptibility related to the dielectric constant and the refractive index as an electric field. Now, the issue is that not all materials respond linearly with electric field. In some cases, the deviation, there is a significant deviation of the plot of the induced dipole moment versus the electric field. And to describe that, you can use a Taylor series expansion, where you expand the dipole moment as a function of the field, and you have the linear term, alpha E, but then you have terms that scale quadratically and cubically with the electric field. And these terms are referred to as nonlinear polarization terms. They give rise to interesting effects, which I'll describe briefly. And they can be used for things like switching and generation of new frequencies using lasers. And so we are interested in understanding in molecules, how do we make molecules that have these nonlinear, in this case it's referred to as the first hyperpolarizability for the term that is quadratic in the electric field, and the second hyperpolarizability for the term that is cubic in the electric field. And the things that are quadratic give rise to what are called second order nonlinear optical effects, and the things that are cubic in field give rise to third order nonlinear optical effects. At the materials level, these are referred to as susceptibilities, and so this is a second order susceptibility, and chi3 is referred to as a third order susceptibility, and that's responsible for third order nonlinear optical effects. Now, just as there is a real and imaginary component to chi1, where the real part corresponds to something related to the refractive index, the imaginary part relates to linear absorption. For chi3, there is something that's called the nonlinear refractive index. And the nonlinear refractive index describes how a molecule's refractive index changes just when it is exposed to an electric field or light. So you can change the refractive index of a material just by shining light on it, and that can be used for all kinds of switching applications. The imaginary part is related to a process that's referred to as two-photon absorption. It is a process where molecules simultaneously absorb 2 photons of light. And those give rise to certain interesting phenomena. And in particular, one of the important things is that if you have a focused laser beam, as I'll show you shortly, you can confine your excitation by and large to where you have the focus of the laser beam. Okay? So for certain applications, we want very large 2-photon absorption. And for other applications, we want a very large nonlinear refraction. And so in some cases, we want a large imaginary chi3. In some cases, we want a very large real chi3. And in the cases where we want a very large real chi3, it turns out that having any 2-photon absorption, any imaginary chi3, is very detrimental. So in some cases, we want to maximize the imaginary part. In some cases, we want to minimize the imaginary part. Well, we're fortunate to have quantum chemists around who can help us describe the essence of third-order nonlinear optical effects in terms of equations that are derived from perturbation theory that relate to optical transitions. These are things that show how electric fields mix excited states with ground states to give rise to change in the electron configuration. And for chi3, this is a very simplified expression, at least for gamma, of that. And it turns out that these materials have terms that relate to the transition dipole moment, the strength, basically, of a transition between ground and excited states. If the molecules don't have a center of symmetry, the change in dipole moment between these states. And there are terms that go between a ground and a first excited state, and terms that are referred to as two-photon terms that involve the mixing of excited states with higher lying excited states. And this we can use to begin to ask, how do we translate these equations, these quantum equations, into molecular structure property relationships so that we can make materials that have the desired properties. Okay, so what I'll first start with is applications that are related to the imaginary part of chi3, i.e. two-photon absorption, and then we'll move to those that are related to the real part. So applications of two-photon absorption, there are many, but I will just focus for the moment on things that take advantage of the fact that when you shine 2 photons of light, as I said earlier, you can get spatial confinement of where you get excitation in a very, very small spatial volume right at the focus of the laser beam. So if that's the case, you can have excitation of fluorescence at a very small spot, and that's used for three-dimensional imaging. It's called three-dimensional two-photon confocal microscopy. There are people who are using this for making three-dimensional optical memory, and there are people who are using this for doing 3D microfabrication. People have heard about 3D printing. This is 3D printing, but on a scale that is on the order of 100 times smaller than what is conventionally done on the small end of 3D printing. Okay? So you can make nanoscopic structures with three-dimensional control. And the way we do that is by activating chemistry in a confined volume in 3 dimensions that changes the property of a material. And I'll describe that as well. So an example of these 3D structures are these photonic crystals that appeared on the cover of Nature in this article a while ago. And what we noticed is that there was really a very significant change in the number of papers published on 2-photon absorption before and after both a paper published in Science the year before this and the publication of this paper, which demonstrated that you can do this process with high fidelity and very efficiently if you have molecules that absorb light in 2-photon processes very effectively. The origin of the 3D resolution is simple. Okay? It turns out that whereas 1-photon absorption scales linearly with the intensity of light, 2-photon absorption scales quadratically. Okay? And that's because 2 photons have to reach the molecule at the same time. Well, if you consider a laser beam and you consider its intensity, as you move away from the focus, the intensity falls off quadratically with distance, which means the 2-photon absorption probability falls off as the 4th power of distance. You can see this right here, where on the bottom we excite a molecule using 1-photon absorption at a wavelength where it's absorbing. And you can see that straight through the cuvette there is fluorescence from this fluorescent molecule. In the top, we excite with 2 photons of half the energy, so that the sum of the energy is the energy that's required to get to an excited state. And what you can see is that when you have this focused laser beam, you only get fluorescence at the center of the cuvette, where you have the focal point of the laser beam. Okay? Well, what we discovered years ago, working with my colleague Joe Perry, is that a very, very simple molecule, this is called a Stilbene, that has donors on the end, ended up having a very, very large 2-photon cross-section, which is the ability of the molecule to absorb 2 photons of light at the same time, relative to a molecule that just lacked these donor groups at the end. There was a factor of 20 increase. And we speculated that that was due to the fact that these donors on excitation move charge to the middle. That rather than there being a change in dipole moment upon excitation in these molecules, there was a change in quadrupole moment. And so we contacted Jean-Luc, and we expressed our speculation, and they went and they did extensive calculations on these molecules. They were able to reproduce the effects that we saw and confirm that indeed that there was a large change in the quadrupole moment of these molecules. And so we speculated that we can design molecules that might even have larger cross-sections than this, which was about the largest cross-section that had been reported for any organic molecule at the time, by increasing the length over which we transfer charge to increase the amount of the change in quadrupole moment, or to increase the amount of charge that we transfer by not only having donors at the end of the molecules, but acceptors at the middle. And so we went and we made these molecules, and Joe Perry went and did measurements on them. And to summarize and simplify many years of work, it turns out that this simple design strategy is robust, and it's now been replicated by hundreds and hundreds of groups around the world. But here is the molecule I showed you. Here is the molecule that has donors at the end. We make it longer, and the nonlinearity, or the two-photon cross-section, gets higher. If we put acceptors that pull electron density, the nonlinearity becomes yet higher. If we make the molecule longer and have acceptors, we see things that are now on the order of 25 times the nonlinearity of what was the best molecule at the time. And so this opens the door to doing a variety of different applications with these molecules, as I'll show you in a second. And it just works as well if you have, instead of things where you transfer the charge from the ends to the middle, from the middle to the ends. Okay. Well, this next slide should have had an animation, but because the computer wasn't talking well, we have a PDF file. But the bottom line is that you can use these molecules to initiate polymerization reactions. And again, you can do it where there's polymerization only at the focus of the laser beam. And you can move that laser beam around, turning it on and off, and you can control, you can build up a three-dimensional image just by having light on in one point and light off on the second point, by, in this case, photo cross-linking the polymer and rendering it insoluble. We were not the first to do this. In fact, Webb did this back in 1992, but the molecules that they had were much less efficient, and as a result, the quality of the structures was very poor. So here are some structures that were drawn by my colleague Joe Perry. Here is a chain link fence. This ended up in a German magazine, Der Spiegel, as the world's smallest fence. There's one in Australia that constitutes the world's largest fence. Okay, these are interlocking parts. Okay, and this square here is the thickness of a human hair. Okay, and that's large on the scale of what we can do. You can make things for photonic applications where you have what are called photonic crossbars. You can make things for microfluidics. You can make surfaces that can be used as templates for tissue engineering. Subsequent to this work and putting this talk together, we also found that we can generate a very, very useful agent using two-photon absorption, i.e. a proton. Things that do that are called photoacid generators. And those can be used to change materials from being insoluble to soluble by breaking off groups. And so using that kind of technique, what we ended up examining is what I call two swimming pools connected underneath the surface, okay, by lanes, tunnels. And so here is an image looking at the top of that, and here are the two swimming pools. And then here's a cross-sectional image looking across, okay, and those are the entries to the lanes, and there's a view underneath the surface. This total distance is that of a human hair. So each one of these lanes are a fraction of the distance of a human hair. And if you asked yourself how you would drill out material like that under the surface, it would be very, very complicated to do using standard lithography, but it's quite trivial to do using these molecules. And the molecules that we've made when you look at their ability to generate acid and the magnitude of the nonlinearity, are on the order of 5 to here 30 times more sensitive than conventional materials. And so what they mean is you can write faster or with much less intensity. Okay? Well, subsequent to this work, this is really kind of taken off, and people all over the world are doing this. And you can see this by virtue of the fact that people like to draw their structures. These are three-dimensional structures: the Eiffel Tower, the Brandenburg Gate, that may be the Statue of Liberty, the Tower Bridge, the Empire State Building. If you're Brazilian, here are things from Brazil. If you like animals, here are bugs. If you like sculptures, here are sculptures. And these are all three-dimensional objects that are basically the size of a human hair. Okay? This is something that's not easy to do by other techniques, and it can't be done by conventional 3D printing. It has to be done using this so-called two-photon 3D printing. And the materials that we have help make this kind of process much more reliable and to be able to be done very rapidly so that you can coat large areas with things like that. So as it was mentioned, we spun off a company, and despite the fact that we were poor businessmen, we were able to sell that and not lose money. Now, let me talk about the real part of the third-order nonlinear optical susceptibility. I give talks to students, and I give talks to even kids, and I tell them they crave bandwidth. And I ask the students, how many of you crave bandwidth? And like 1 or 2 people raises their hands, and I said, I will bet you that you all crave bandwidth. Okay? And I ask people, how many of you have downloaded a full-length feature film? And some people kind of sheepishly raise their hands that they've done it. And it takes some time. And the reason is that we don't have sufficient bandwidth. Bandwidth being the amount of information per unit area, per unit time, that we can send through a cable or a fiber optic. And indeed, if you look at the amount of exabytes that we're using per month, it's just going up dramatically. And this is limiting data transmission rates. And the other thing which is happening is that when you go to places that are the data centers of the world, they're all now located very close to large water sources because they generate huge amounts of heat. They're using actually multiple % of the United States electricity budget per year. Okay? And that's because they're not all that efficient. Well, I will just assert without defending that if you communicate using light, you can get much higher bandwidths, and you can avoid having to convert light signals to electrical signals back and forth, and you can use less electricity. And so in order to do that, you need to be able to manipulate light in much the same way that transistors, for example, manipulate electrons. And there are materials that can do this, and these are so-called Chi3 materials working on the real part of Chi3. And the way this can work is you can imagine splitting light into 2 paths, and then they can recombine, and they can recombine constructively or destructively. If in one arm of this little device that's referred to as a Mach-Zunder interferometer, you change the index of refraction, you'll accumulate a phase shift. Okay? And what that means is that if you change that index of refraction enough that you can accumulate a 180-degree phase shift, you can get destructive interference. And so what you can do is you can take an optical signal, and then you can take a pulse of light with this third-order material, and that pulse of light will change the refractive index. And when you do that, you can control whether you have destructive or constructive interference, and you can modulate the light at very, very high frequency. And this is a very important part of being able to do all optical switching. Now, the challenge is that the real part of Chi3, that nonlinear refractive index, over the imaginary part, the thing that we were trying to make big in the previous part of the talk, has to be greater than 12. And it turns out that for all molecules pretty much that had been examined for years and years and years, it was very, very hard to find things where that was true, to the point where it damn near killed the field. Okay? People gave up. And as it turns out, that doesn't have to be the case. And so we developed over a period of years a model for what's going on with nonlinearities based on the notion that if we look at a polyene or a polymethine chain, we can, which has single bonds and double bonds, we can have a parameter that we refer to as the bond length alternation. We can have short bonds and long bonds. And by controlling that, we can control the optical nonlinearities. And for polyenes, we have a very, very large degree of bond length alternation, or bond order alternation, where the bond order of a double bond is 2, and the bond order of a single bond is 1. But as we introduce polarization into the chain, we can change that. And so in simple polyenes, you end up having what are referred to as resonance forms, and you can have one which is neutral, one which is charge separated, and in those kinds of molecules you end up with a very large degree of bond length alternation. When you start putting donors and acceptors in these molecules, you can tune that down, and if you make these molecules such that you have actually a very strong acceptor on one side and a very strong donor on the other side, you can get to the point where both forms of the molecule are equivalent in energy, and this so-called bond length or bond order alternation goes to 0. So this is something that we can tune, and working with Jean-Luc and one of my former postdocs, Chris Gorman, and some other folks, we went and in the computer, we systematically varied the bond length, the bond order alternation, from something that looked like a polyene to something where we had a high degree of charge delocalization, which we refer to as a cyanide, to something where it was actually very charge separated. And what we found is that if you look for the linear polarizability, it starts out small at the cyanide limit, which is this point where we have equal charge distribution on both sides of the molecule and 0 bond order alternation. It's very high. And then we looked at the first type of polarizability, and we discovered that it starts out very small, it becomes large, it goes down, it becomes 0 at this so-called cyanide limit, and then it becomes negative. And then we looked at the third order nonlinearity, and we found that it starts out small, it becomes positive, it becomes very large and negative here at the cyanide limit, and then it becomes positive again. And we looked at many molecules and we mapped out these structure property relationships, and we showed that they worked. And we said, these cyanide molecules look very interesting. Now I won't dwell on this slide, but I can tell you that by doing the calculations, we can get a very, very detailed understanding of the spectroscopy of these molecules and all of the detailed contributions that enables us to design these molecules to have very precise structures and to get to the cyanide limit and the maximum nonlinearity. So these dyes called cyanides have very large nonlinearity. The nonlinearity increases with length. They have very sharp absorption bands, which means that you can get materials where you don't have much what's called linear absorption, one photon absorption. They can aggregate because they're amongst the most polarizable molecules known. And they can undergo a process called symmetry breaking, where they no longer hold this very, very symmetrical structure. So in our program, we were looking at these molecules, and what we found out is that there's a molecule which is a cyanide-like molecule, had a very large nonlinearity, had a very large chi3, all of which was very good. And what we didn't realize, although we should have, is that if we get the molecule can simultaneously at one energy have a very large two-photon absorption, but this is the thing that we didn't appreciate. If you move away from that, you can have a point where there's almost no two-photon absorption. And that's exactly what we want for all optical switching. I won't go into the details of why these molecules have that property, but it has to do with the spacing of excited states. And cyanide molecules end up having a large spacing between one excited state and a higher excited state so that we can put 2 photons of energy in between and it doesn't get absorbed by this state or by that state. Okay? And that turns out to be really important. So we designed molecules that did that. And remember, we were looking for molecules that had a real to imaginary nonlinearity ratio of 12. This one that I show here gave 10. We went and made other molecules through some careful design parameters where these ratios are on the order of 95 or 190. So now we're really cooking with gas. This is what we really want to be able to do. We had the molecules, but there's a problem. And the problem is that these materials are highly polarizable and they tend to aggregate. And when they aggregate, they end up creating additional excited states depending upon how they aggregate. And so here we design these molecules to have a large open space between the first and the second excited state. And then when you start allowing them to get together in various different ways, all these little states get in and it completely kills it. That's illustrated on the next slide, where I show you, and this is a complicated slide, okay? There's a curve that goes like this, very sharp, very nice. That's the solution. You put this in the solid state, and all you need to see is that these bands look very different than this solution band. And we began to build things off of it that were sort of floppy to try to keep them from getting close together, and it didn't work. So we took an approach where we took a molecule, we said we need to go and we need to put rigid things on there that will effectively be like bumper cars that keep the molecules from aggregating. And if you put things in the middle and the front and the back, that will keep them from getting too close, but they can overlap at the ends. If you put things on the ends, then they can overlap like that. So we needed to come up with things that really prevented all forms of aggregation. And indeed, we were able to do that. We were able to put things, here is with nothing on this molecule that was great in solution, and it looks like that in the solid. You put things in the middle, it doesn't look very good. You put things on the end and the middle, then we start having solid spectra of these compounds that look like the solution properties. And so now we can begin to hope that these will have the properties that we need. And indeed, they do. When we look at these materials, in the solid state, we start seeing the figures of merit that we need. We have very large figures of merit. In some cases, the loss is not great, but it's getting close to where we need it to be. So what we discovered is that we can take some of these molecules, and if you have nothing in the middle, you get a lot of interaction between the molecules. These are from crystal structures, which is not good. If we put this organometallic group on the system here, which is a palladium and 2 what are called phosphines, phosphorus, with 3 large groups on it, these 3 large groups completely cover the top and the bottom of the molecule, and they separate them out. And using that strategy, what we were able to do is make molecules that had very large nonlinearities, good figures of merit, and now the linear loss is we put these into a polymer. The linear loss is indistinguishable from the polymer. We have no molecules. So now we're at a point where we can do applications based on these molecules, and the very first one was done by colleagues at the University of Arizona. If you have a fiber and you send light through it, there's a process that's called self-phase modulation, and really all you need to know is that when you have self-phase modulation, you can send in a pulse that is very narrow in the line width, and then as it goes through the fiber, due to the nonlinearities in the fiber, you'll see that the pulse broadens to a large number of wavelengths. And there was a guy who has a fiber laser company who was interviewed in Nature Photonics, and he said, boy, wouldn't it be great if we could have materials that had no nonlinearity. So here I spent a career making materials with large nonlinearities. Wouldn't it be great if we had no nonlinearity? Then things would go through the fiber very well. And so we ended up making molecules that had negative nonlinearities. And so if we mix those in with the solution that is positive, we can exactly cancel the nonlinearity. And what you can see here is that when you do that, okay, this broadening completely goes away, and we can cancel that out. And so that's something that we're exploring for high power fiber transmission applications. Okay, so what I'm trying to show you here is, I'm summing up 25 years of research in 35 or 40 minutes. The third order properties are not simplistic. There's real parts, there's imaginary, there's positive, there's negative. But we can systematically engineer them if we understand how to design the molecules, and in this case, based on first principle quantum mechanics and some chemical intuition. For two-photon absorption, these donor-acceptor-donor molecules have large two-photon cross-sections, and now there are commercial 3D microfabrication systems using two-photon microfabrication based on the kinds of things that we've looked at. Cyanin molecules can be very, very good for having a large real part of Chi3 and very low two-photon absorption. And what we speculate for the Chi3 is that through combinations of novel device designs, we can't do this just with materials, that we can have third-order nonlinear applications based on all optical switching that will become feasible. And that's where we're working today. So with that, I'd like to thank you, and we have a minute or two for questions if we're trying to stay on time. And again, thank you very much for coming late in the day and listening to this.
This mic is sort of on. Thank you, Seth. You took some real complex optics and molecules, and you could track it through.
Yep.
For some of your applications, are these conjugated systems going to be stable for the lifetimes you're going to need? So
we do not know for the third order materials, but for the all optical switching. But when you've sent them, when we've put them into the liquid core optical fibers, you're putting a lot of energy through there, and those things are holding their own.
Great.
We're ultimately going to keep them from light, well, not from light, but from oxygen, if we can, and we think that that's completely doable.
Time for one other question, so we don't eat up the next speaker's time. Please, come to the mic if you would.
You kind of mentioned it, but I wanted to be clear about it. Does the need for non-symmetric molecule that is required for second-order nonlinear optics is also required here?
No, not at all. In fact, it's all of the even-order nonlinearities, second order, fourth order. You have the requirement for non-centrosymmetry. For all the odd systems, first order, third order, fifth order, you do not have that requirement at all. And in fact, some of the systems that are most promising tend not to have donor-acceptor charge transfer interactions for the real part of Chi3, because those lead to very large two-photon absorption.
Please join me again in congratulating Professor Marder.
Thank you.